Indiana University East Physics P120 P125, the biological effect of radiation. So far we have talked about the various types of radiation, and in terms of radioactivity we are mostly concerned with alpha, beta and gamma radiation, and remember what they are. What I really want to do now is to talk about how they cause damage. Okay, and to do this I first need to explain what free radicals are. Okay, so the definition of free radical is that they are highly reactive species. Okay, they're chemical species, so they could be atoms. Well, not so much atoms. Atoms, I take that out. They're going to be molecules or ions, typically. Remember, ions are charged atoms or molecules. Okay, and the key feature about them is that they have an odd number of electrons. It turns out that chemically speaking, anything with an odd number of electrons is extremely reactive. Okay, and so what radiation actually does is that it forms these free radicals, which in turn leads to greater damage to molecules that are relevant to everyday life. In this video, what I'm going to do is I'm going to look at the mechanisms by which this occurs, and then go into a little bit more on how this might happen. So in terms of alpha and beta particles, remember alpha particles are helium nuclei, and beta particles are electrons from the nucleus. And the key feature about them is that they're at very high speeds. Alpha particles usually are moving at 1/10 of the speed of light, and beta particles usually are about 90% of the speed of light. So this is a key point. So what happens is, I'm going to use the alpha particle as an example. The beta particle pretty much operates the same way. Alpha particle goes near a molecule, okay, I'm just going to represent it with something like this. And it's positively charged, right? It has a +2 charge. So this +2 charge attracts an electron. Which basically drives the electron away from this atom. But here's the catch. Yes, the electron is dragged towards the alpha particle, but the alpha particle is moving so fast this electron can't catch up. So this electron is then bound to a different nucleus. So now you form, now this atom itself, okay, loses one electron. And when it loses one electron, it forms a positively, because it's an electron, right? So this is negatively charged. So we're left with a positively charged radical ion, because it now has an odd number of electrons. Similarly, the atom, or molecule that the electron is now bound to is now negatively charged. Okay. In terms of beta particles, it's pretty much the same thing. Now this time it's not attracted, but rather it's both the electrons and the beta particle, because the beta particle is an electron after all, will repel each other, and by this interaction it will drive it out of the atom that it's in, and hence it forms a radical ion. gamma radiation. As you may remember, gamma rays, we're talking about electromagnetic radiation with an energy of about 2 times 10, 6 times 10 to the minus 14 joules. What does it do? Okay, so it might get absorbed. So this is my gamma radiation, and I've got my atom or molecule here, and it turns out, if you think about this, it turns out that the energy required to remove an electron from an atom is about 2 times 10 to the minus 18 joules, at least for hydrogen atom. So this gamma radiation, if it gets absorbed, the electron is removed from the atom, and we are left therefore with a positively charged radical cation, or positively charged ion. Cation is just a fancy word for positively charged ion. Okay, so we are now going to talk about how biological damage occurs. There are 2 ways by which this occurs. Now, the first thing I'm going to say is that I'm going to focus on gamma radiation, because gamma radiation is the least damaging, but it is actually the most dangerous because it penetrates everything. I can block alpha radiation with my skin. I can't do that with gamma. And gamma radiation, it can go anywhere. It goes through concrete, okay, and eventually it gets one of 2 things. One is, and the most damaging thing it can hit, of course, is DNA. And depending on which part of the DNA it hits, it can lead to various types of damage. So this is direct absorption of gamma radiation by DNA. And what this does, it leads to base destruction and strand breaks. So you can either destroy the DNA bases, so now we have no base. It's like leaving a blank in your genetic code, which doesn't help. Or we can break the DNA backbone. Okay, so here we've got a strand break. So this is very damaging. The other thing you can have is an indirect effect. DNA, how should I put it? DNA doesn't really, we don't comprise a lot of DNA. Most of what we comprise of is water. So what can happen, importantly can happen, is that water can be ionized. So water, instead of DNA absorbing the radiation, we have water absorbing the radiation. Now, if water absorbs the gamma radiation, it basically spits out an electron, okay, which forms what we call a hydrated electron eventually. And so it's basically an electron in a water cage. In addition, we have the water radical cation. These can cause a lot of damage. They then produce, these are the most commonly found species that can damage things. So we got the hydrated electron. We've got hydrogen radicals. And we've got hydroxide radicals. So this is important because it's HO, okay, but it doesn't have a negative charge. It is not a hydroxide ion. It's a hydroxide radical. And we can also form hydronium ions. These species are all very reactive. H3O plus probably the least so, because it exists anyway. But all of these can cause significant damage to biomolecules such as DNA strand breaks. So the point is that you don't need the radiation to directly hit biomolecules to cause damage. You can hit water, and water can basically cause secondary damage through reactions of water and these reactive species interacting with our biomolecules.